I want to provide a schematic to help you think about a pitchfork bifurcation. So in this schematic, my parameter is the load. The load is going to start small, it's going to get bigger, and then I'm actually going to decrease it again. And the state of my system is going to be what's going on with this beam. So you can see that in this image, the beam is taking on two different states. Part of the time, it's just completely straight. Think of that as kind of the origin, the basic state. And then depending on the load, it might be bent either to the right or to the left. And that bending in either direction, that's the pitchfork idea, that there were two choices that it could bend. And so what's happening here is when the load is small, my beam is straight. And then when the load gets a little bit bigger, my parameter increases, my beam is still straight. But when the parameter gets even bigger, it's actually too much for my beam, and my beam bends just a little bit. However, this bend is reversible. If I reduce the parameter, I'll return back to my old state. So that's typical of supercritical bifurcations, that the state changes as I change the parameter, but that's reversible if I change the parameter back. Now I want to extend the schematic to a new case called the subcritical case. In the subcritical case, things look similar at the beginning as we're initially increasing the load. The state of the system doesn't change. However, when we increase the load past the bifurcation value, for a subcritical bifurcation, instead of this reversible change that we recover from when we reduce our parameter, we go through a change that's less reversible. In this case, you could think of that as the beam buckling, rather than the beam bending a little bit. And once the beam buckles, even if I reduce my parameter back to its original load, the beam doesn't easily recover. Now I'm going to construct the bifurcation diagrams, first for the supercritical case, and then for the subcritical case. The bifurcation diagram shows fixed points where dx dt is 0 versus the parameter r. There are three qualitatively different cases as r changes sign, and I want to explain how we create these kind of curves that allow us to think about those different cases. So first, let's think about when x is big. When x is big, Rx is going to be pretty small compared to negative x cubed. And so out at large x, I want the function to have kind of a negative x cubed type shape. So it's going to be positive and growing when x is negative. It's going to be negative and decreasing when x is positive. And you can see these little kind of green lines that are indicating what's happening at the large x. Then I want to think about the small x limit. Now, when x is really small, x cubed is going to be super tiny, and Rx is going to dominate what we see for the right-hand side. So let's see. If Rx is dominating, when R is negative, right near the origin, where Rx is dominant, I want a negative slope. When R is 0, I want a slope of 0 as we pass through the origin. And when R is positive, I want a positive slope for those small x values as I pass through the origin. Once I know what's going on at the origin and at the large limit, I use kind of my basic knowledge of the shape of cubics to draw a line or a curve that connects these up. For each of these pictures, I go ahead and mark the fixed points. I add arrows showing the direction of the flow at different points on the x-axis, and I indicate the stability of the different fixed points. Next, I'm ready to take this information about the fixed points and their stability and put it into a bifurcation diagram. For r less than 0, the origin is a stable fixed point, and when I'm at a particular value of r, solutions are going to flow towards the origin. When r is equal to 0, the origin is still a stable fixed point, in this case algebraically stable instead of exponentially stable. Solutions are still flowing to the origin, albeit more slowly. And then here we are at a positive value of r, and we have that unstable fixed point at the origin, our pair of stable fixed points, and flow pointing away from the origin towards our stable fixed points. So those are the three cases that we saw above. But the bifurcation diagram actually is for all values of r, and so I've had to solve for the fixed points in terms of R to find these curves and draw them onto the diagram. In the example that we've just done, the supercritical pitchfork opens in this direction with an initial stable state that branches into two possible stable choices while that initial state became unstable. We still call it a supercritical pitchfork, even if it opens the other way. The thing that makes it supercritical is the fact that this new pair of states is a stable pair of states. Now let's take a look at the subcritical example and see how its bifurcation diagram is different. Again, we think about large X to get these little green lines, and then we think about small x and its dependence on R to understand what's happening right at the origin. So I've changed from a minus sign to a plus sign to go from the supercritical to the subcritical pitchfork, and that impacts what's happening out at large X, but it doesn't change what's going on near the origin. Again, I go ahead and draw in my fixed points. I draw in the directions of flow at different points along the x-axis, and I basically create my phase line for my different scenarios. I again solve to find the fixed points of x in terms of R and get those curves onto my bifurcation diagram. So this is the R positive case. I have a fixed point at the origin and it's unstable. This is the R negative case. I have a fixed point at the origin and it's stable. If you just look at what's going on with the origin, this looks just like my supercritical case. Over on this side, things were stable. Over on this side, they were unstable. However, now when I pass through the bifurcation, instead of stable branches being born, my stable state disappears and no obvious new stable structures appear. That means that if my parameter changes so that I go through the bifurcation, it's not really clear according to this model what the new state of my system will be. In fact, according to this very basic model, the state of my system is simply going to head off to positive or negative infinity. I would just think of that as the state of my system is leaving the range in which this model of the system makes sense. Just as for the supercritical case, for the subcritical case, things can happen in either direction, and the thing that makes it subcritical is that the new states that appear at the bifurcation are both unstable. So in the supercritical state, the new pair of states was a stable pair, and in the subcritical case, the new pair of states is an unstable pair.